Welcome to the subject Agronomy 1. This is Lecture 7, an introduction to fertility and crop nutrition. This subject is taught as part of the Bachelor of Agriculture and Technology and the Bachelor of Equine Studies. These degrees are offered at Melbourne Polytechnic, with the Bachelor of Agriculture and Technology being offered in a partnership with La Trobe University. To find out more about this course and the other courses that we offer, please visit our website at www.melbournepolytechnic.edu.au. My name is Dr. Nikki Cooley. In Lecture 7, we hope to give you the basics of the essential elements, that is, an overview of the macro versus the micronutrients. Please remember we have covered the macronutrients nitrogen, potassium and phosphate in Lecture 6, and I would strongly encourage you to review Lecture 6 before commencing Lecture 7. We will talk about the beneficial elements and how the plant growth can be promoted by these beneficial elements. I'd also like you to refer to Lecture 6, the law of minimum. This is an important component and does apply here for micronutrients as much as it does for the macronutrients. And we will finally touch on fertility and the science. Please note that the recordings of this lecture will be in several parts, as it is too long to record in one part, and this is part 1. As we learnt in Lecture 6, part 1, soil scientists have long demonstrated relationships between soil fertility in the soil and plant tissue and yield. In many situations, it is our aim to optimize certain aspects of plant growth as they are the most commercially beneficial. For example, if we are growing a wheat crop and we want to sell this wheat crop as bread, we are aiming for a high quality grain yield. That is, not only do we want to create lots of grains, but we want a good proportion of the right proteins and other chemical characteristics that enable good bread production from the grain. However, if we are growing a crop such as potatoes, we are interested in large tubers, and this is quite different to that of the bread example. Therefore, when you are thinking of fertility and science, you should always look at your economic return. What are you ideally trying to do? Sometimes you will need to manage nutrients because of secondary components of your economic return. It has long been established that in most situations, the more nutrients you put on, the higher the yield you will get. However, there is an optimal amount of nutrients to be applied in many situations. That is, you can apply more and more nutrients and not get a better yield because there are other components in your production system that are limiting, perhaps water, for example. There is also an economic component that you must consider when thinking about your nutrients. You want to add enough nutrients to optimize your commercial yield. But at the same time, you do not want to spend too much money on this, otherwise your production costs will be increased and your economic return as a result will be reduced. Therefore, nutrient management is always going to be a balance. So you can separate soil fertility into the macro and micronutrients, and this is one form of classification. I will note at this point there are other classifications, but we won't be using them in this topic. They are covered in other subjects across this degree. So we have covered some of the basics of the macronutrients in Lecture 6. We looked in detail about nitrogen, potassium and phosphate. We looked at the cycles of all of these nutrients and how they are used in agronomy. In this lecture, we will concentrate on the macronutrients that we did not include in Lecture 6 and the micronutrients. There is a question that you might be thinking, are the macronutrients more important than the micronutrients? And this indeed is a reasonable question, and something that we will be exploring throughout this lecture. Essential elements are required in large quantities, while others are in smaller amounts. Many of these elements are found in sufficient quantities in the soil and no amendments are needed. The primary nutrients consist of nitrogen, potassium and phosphates, and these are usually required in large quantities. All other nutrients are secondary. Okay, so the macronutrients are nitrogen, potassium, phosphate, calcium, magnesium and sulfate. Today in this lecture we are going to look specifically at calcium, magnesium and sulfur, as these we did not cover in lecture 6. The macronutrients magnesium, calcium and sulfur are defined as macronutrients as they are usually required for most plant growth to be in larger concentrations than the micronutrients. You must always remember that when we are referring to how much or the concentration of nutrients, we are not just talking about the nutrients in the soil per se, but actually what is available to the plant. So not only must the micro and macronutrients be available chemically, but there usually has to be at least a small amount of water to enable the uptake in plants. The micronutrients include chloride, iron, boron, magnesium, zinc, copper, molybdenum and nickel. There are some debates about a few other compounds, but we won't cover them here. It is a safe assumption that most micronutrients in most growing situations are required in small concentrations. But as you will learn later on in this lecture, parts 2 and 3, that doesn't necessarily make them more important or less important than the micronutrients. Sulfur, calcium and magnesium are considered secondary metabolites because they are less commonly yield limiting than the primary macronutrients, yet they are required by crops in relatively large amounts. So what this means is that in most soils you find adequate concentrations of sulfur, calcium and magnesium, so you don't have to worry about them. Many of the soils in Australia and around the world indeed do show adequate secondary nutrients for crop production. But sulfur deficiencies can arise in both the US regions and in other regions throughout the world, as stated by Ramson and Kersage in 1986. 3 global trends are responsible for increasing sulfur deficiencies. The first is there is a shift in modern fertilizations practices to more concentrated and higher analysis forms containing little or no sulfur. That is a historical byproduct of the manufacturing process used to have sulfur, and it no longer does. So that's your first problem leading to sulfur deficiencies. Secondly, the reduction of sulfur dioxide emissions from burning coal and oil, which decreases atmospheric sulfur additions, has occurred. So that's good from a pollution perspective, but not so good from our farming perspective. And thirdly, the steady increase of crop sulfur uptake and removal due to high-yielding varieties and more productive management systems is depleting the existing soil sulfur concentrations, and this has led to deficiencies. Effective management of secondary nutrients requires an understanding of the processes that determine their availability in the crops and methods to manage soil and inadequate secondary nutrient levels. Also, large amounts of calcium and magnesium are added when lime is applied to acidic soils. Sulfur is usually found in sufficient amounts, and the slow decomposition of soil organic matter, an important reason for not throwing out the grass clippings and leaves. So let us start with calcium. So what is the role of calcium in plants? Well, it is an essential plant nutrient, and it is essential because it is involved in many roles. It participates in the metabolomic processes of other nutrient uptake. It promotes proper plant cell elongation. It strengthens cell wall structures. Calcium is an essential part of the plant cell wall. It forms calcium pectate compounds which give relative stability to cell walls and bind cells together. It participates in enzymatic and hormone processes. Calcium is found in protecting the plant against heat stress. Calcium improves stomata function and participates in induction and heat shock proteins. Calcium is used in protecting the plant against diseases. There are numerous fungal and bacteria secrete enzymes which impair plant cell walls. Stronger cell walls induced by calcium can avoid this invasion. Calcium can affect fruit quality. It has a role in the regulation of stomata. Calcium regulates the transport of other nutrients into part of the plant and is also involved in the activation of certain plant enzymes. Calcium deficiency results in stunting. The nutrient is involved in photosynthesis and plant structure. Blossom end rot is also a result of inadequate calcium. There are factors that affect the availability of calcium to plants. Calcium forms insoluble compounds with other elements in the soil, such as phosphorus. Calcium that is in that form in an insoluble compound is not available to plants. Since calcium is a positively charged ion, it is absorbed in the soil to the surface of clay and organic particles, which are negatively charged. Positively charged ions absorbed to soil particles are termed exchangeable ions because they can be exchanged by other ions present in the soil solution. Soil analysis determines the level of exchangeable calcium ions and not the total calcium in the soil because the exchangeable calcium is in the form which is available to the plant. Several factors in the soil analysis can help in assisting the availability of calcium to plants. Soil pH, for example. Usually soils with a higher pH level contain more available calcium. CEC is a soil characteristic that describes the total amount of positively charged exchangeable ions that a soil can hold. A higher CEC indicates a higher capacity of the soil to absorb and hold calcium, and therefore higher calcium availability. The presence of competing ions. If calcium competes with other positively charged ions such as sodium, potassium, and/or magnesium, therefore applying too much of these positively charged ions might actively decrease calcium uptake in plants, because they're all competing for the negatively charged ions that are in the soil. Sodium ions can replace the absorbed calcium, damage soil structure, and decrease calcium availability. While calcium is an essential element for all plants, the following crops that you can see on your slide have been found to be especially responsive. These include apples, broccoli, Brussels sprouts, cabbage, carrots, cauliflower, celery, cherries, citrus, conifers, cotton, cucurbits, melons, grapes, legumes, lettuce, peaches, peanuts, pears, peppers or capsicums, tomatoes, tobacco, and potatoes. So let us see how we may detect a calcium deficiency. Well, there are phenological indicators that some plants can show. Calcium deficiency symptoms can be rather vague sometimes, and so the situation is often complicated by a low soil pH. So if you suspect a low calcium, the very first thing and probably the easiest thing you can do is check the soil pH. If it's acidic, then it's more likely to be a calcium deficiency. Visible deficiency symptoms are seldom seen in agronomical crops, but will typically include a failure of the new growth to develop properly. Annual grasses such as corn will have deformed emerging leaves that fail to unroll. The new leaves are often chlorotic. Extremely acidic soils can introduce an entirely new set of symptoms, often quite different toxicities and deficiencies, and this can complicate detection. Many fruit and vegetables demonstrate dramatic symptoms such as black heart in celery and broccoli and tip burn in lettuce and cabbage, white heart or hollow heart in cucurbits, blossom end rot in tomatoes and peppers, and pops in peanuts. Tree fruit with low calcium will exhibit increased storage problems such as a bitter bite taste, cork spot in apples and pears, cracking in cherries, and other degradation of the fruit while in storage. Deficiency in all crops often also impairs root growth and leads to additional symptoms as a secondary effect. Calcium deficiency in conifer trees will exhibit yellowing, then death and dropping of the needles on the new growth. The new growth may also be deformed. On your handouts I have included a couple of interesting resources. It is not essential that you read these on diagnosing calcium deficiency in barley or the Government of Ontario overview of calcium. They are just there for your reference and knowledge. Calcium plays an important role in cell elongation and maintaining membrane structure in plants. The presence of calcium in roots also regulates plant cation uptake by limiting excess sodium and increasing beneficial potassium absorption. Most soils, especially those in Montana or Wyoming, for example, in the US, contain abundant calcium in the solution between 30 and 300 parts per million. And this is relative to most crops' requirements at approximately 15 parts per million. The supply of calcium in a soil solution can be 10 times larger than potassium, and plants require much less calcium, so deficiency is rare. Mass flow supplies adequate calcium to the plant roots, except in low calcium soils, where diffusion becomes an important process. These two descriptors describe how the nutrient gets to the plants and into the plant root. Calcium is usually the dominant base cation in exchange reactions, accounting for more than 70% of the base saturation. The base saturation represents the percentage of the CEC occupied by the base cations, that is calcium, magnesium, potassium and sodium, and generally increase with pH. Exchangeable calcium exerts in equilibrium with the soil solution, replenishing soluble calcium losses by the plant uptake or leaching. Leaching can be significant in coarse textured acidic soils where substantial water moves through the profile. In many calcareous soils, some calcium leaches out of the more acidic organic-rich topsoil and precipitates into the calcic horizon in the subsoil in the form of calcium carbonate, CaCO3 is the formula for that, or in the form of gypsum, which is CaCO4. In addition to the dissolution of secondary deposits, calcium is also released through the weathering of primary minerals, such as feldspars, nickel, and limestone, all of which are common throughout many regions. Low calcium content in soil often causes acidity problems before actual calcium nutrient deficiencies become an issue. Both the role of calcium as a base cation and its frequent occurrence with carbonates, CO3, CO2, and bicarbonates, HCO3, buffer soil in high pH levels. Where acidity is a problem, limiting soils with calcium carbonate, CaO, and CaOH2 is a common practice. The role of pH in nutrient cycling and how it can be managed will be discussed in greater detail in other subjects. Because of its strong divergent charge, calcium acts as an ionic glue, attracting clay particles and promoting aggregation through a process called flocculation. I don't expect you to understand this at this point in the course, but you will be introduced to these concepts later on. Soils with a high level of sodium, referred to as sodic soils, promote dispersion, which is the opposite of flocculation. When monovalent, that is single charge, sodium ions dominate the clay surfaces in the soil, the weak positive charge on the ion is not yet strong enough to overcome the negative charges in the clay particles, which then repel each other. The result of dispersion is that structureless, gel-like soil with insufficient aeration, permeability and water holding capacity for optimal plant growth occurs. Additions of calcium in the form of gypsum are frequently prescribed for reclaiming sodic soils because it contains the effect of sodium and promotes aggregation, critical for soil productivity. Gypsum is preferable to calcium carbonate because gypsum is more soluble. Low sodium irrigation water on rainfall can be used to leach sodium out of the profile as another management technique for managing this situation. Nutrients can interact with each other, and in fact calcium is commonly found interacting with other nutrients. That is, calcium can interact with other cations. Being a major cation, calcium availability is related to the soil measurement CEC, and it is in competition with other major cations such as sodium, potassium, magnesium and ammonium, as well as iron and aluminium. Therefore, a mineral will compete with all these other positively charged minerals for plant crop uptake. High potassium applications have been known to reduce the calcium uptake in apples, which are extremely susceptible to poor calcium uptake and translocation within the apple tree. Calcium can interact with sodium. High levels of soil sodium will displace calcium and lead to calcium leaching. This can result in poor soil structure and possibly sodium toxicity to the crop. Conversely, applications of soluble calcium, typically as gypsum, are commonly used to desalinate sodic soils through the displacement principle in reverse. Calcium can interact with phosphorus. As the soil pH is increased above pH 7, free or uncombined calcium begins to accumulate in the soil. This calcium is available to interact with other nutrients. Soluble phosphate is an anion, meaning it has a negative charge. Any free calcium reacts with phosphorus to form insoluble or very slowly soluble calcium phosphorus compounds that are not readily available to the plant. Since there is typically much more available calcium in the soil than phosphorus, thus interactions nearly always result in less phosphorus availability. Calcium can be found interacting with iron and aluminium. As the pH of a soil decreases, more of those elements become soluble and combine with calcium for the essential insoluble compounds. And finally, calcium can interact with boron. High soil or plant calcium levels can inhibit boron uptake and utilization. Calcium sprays and soil applications have been effectively used to help with toxicity of boron or where boron is over-applied. There are claims in the scientific literature that it is not only about the concentration of the nutrient in the soil, but rather that there are what we call ideal ratios of several soil components that help plant growth and nutrition. So let us look at the calcium balances and ratios. There are a few people that claim that there is an ideal ratio for the three soil cation: potassium, calcium and magnesium. This concept probably originated from New Jersey work in Bear in 1945 that projected an ideal soil as one that can have the following saturations of exchangeable cations. It stated 65% calcium, 10% magnesium and 5% potassium, where there was 20% hydrogen. The cation ratios resulting from these idealizations concentrations then become a 6 to 5 to 1 ratio. It is generally accepted that there are some preferred general relationships and balances between soil nutrients. There is also a significant amount of work indicating that excess or shortage of some nutrients will affect the uptake of other nutrients. However, no reliable research has indicated that there is a particular soil ratio of nutrients that can result in a uniforming hypothesis. Over the years, a significant amount of conversation and salesmanship has evolved around the concept of ideal calcium-magnesium ratios. Most of the claims for ideal ratio range from 5 to 1 and 8 to 1. Some of these claims are that the correct soil calcium-magnesium ratio will improve soil structure, reduce weed populations, especially foxtail and quickgrass where they may grow. Plus, they can improve foliage quality. This all depends on where you are located as to the benefits, of course. It is also claimed that the calcium-magnesium ratios, when ideal, can reduce leaching of other plant nutrients. It generally improves the balance of most soil nutrients, according to Dr. Stanley Barber. At a conference, he was once stated, "There is no research justification for the added expense of obtaining a finite calcium-magnesium ratio in the soil research. In fact, research indicates that plant yield or quality is not appreciably affected over a wide range of calcium-magnesium ratios in the soil." Wilson research found that yields of corn and alfalfa were not significantly affected by the calcium-magnesium ratios ranging from 2.28 to 1 to 8.44 to 1 in all cases. When neither nutrient was deficient, the crop's internal calcium-magnesium ratio was maintained with a relatively narrow range consistent with the needs of the plant. These findings are supported by most other authorities. A soil with the previously listed ratios would most likely be fertile. However, this does not mean a fertile soil requires specific values of these ratios. Adequate crop nutrition is dependent on many factors other than a specific ratio of a couple of nutrients, and it is important to remember this. So, how can you apply calcium as a fertilizer to the soil? Well, most commonly there are three commercial products that you can consider using: lime, gypsum and calcium nitrate. Lime, CaCO3, has the advantage that it is both a calcium fertilizer and a pH correction, and if you need to correct your pH, this will help your plants uptake other nutrients. Its disadvantage is that it's less soluble and less reactive in non-acidic soils. You can consider the product gypsum, known as calcium sulfate. The advantage is it's both calcium and sulfur nutrients, and it can also assist with the flocculation of clays. The last product, calcium nitrate, is a non-acidifying nitrogen fertilizer, as well as a calcium fertilizer, but alas, it is an expensive product. Now let's move on to another micronutrient, magnesium. This is represented by the chemical symbols Mg. Magnesium has a number of functions in plants. Its probably most commonly reported and perhaps most important component is it is one of the central components of chlorophyll. If you remember, chlorophyll is the structure in plants which enables the light capture of energy and then will go on to convert into chemical energy. It is also important in ATP, though it has a role as an enzyme cofactor. Magnesium has a role in respiration and nucleic acid formation. Magnesium deficiency can result in intestinal chlorosis. Magnesium deficiency may be a significant limiting factor in your crop production. Let's look at magnesium's role in the soil. Well, like calcium, it can occur in the soil as a soluble divalent. That means double-charged cations. And it has cation exchangeable sites in its mineral forms. The major processes of the calcium-magnesium cycle are plant uptake, exchange, precipitation, weathering, and leaching. Calcium-magnesium dynamics in the soil are quite similar to that of potassium. Like potassium, plants absorb the soluble ionic form from the soil solution, which is then replenished by exchangeable and mineral calcium-magnesium ions. The most notable difference between those nutrient cycles is the absence of calcium-magnesium clay fixation. Magnesium plays a critical role in nearly all parts of plant metabolism and protein synthesis, as cited on the previous slide. Mineral forms of magnesium are relatively resistant to weathering and represent a large fraction of the total soil magnesium. You can find magnesium in mineral forms in the soil, and these include biotite, hornblende, and olivine, dolomite, and most 2-to-1 clay minerals. Soluble magnesium can also precipitate out of the solution to form magnesium carbonate or magnesium sulfate, frequently along with magnesium carbonate in the subsurface. Although calcium and magnesium share the same exchangeable processes, magnesium absorbs less strongly to soil colloids and therefore is more prone to leaching, particularly in sandy soils. As a cation, manganese competes with calcium, potassium, and NH4 for the absorption of plants. This is because competition occurs at the cation exchange sites. Magnesium deficiencies occur when there are other cations dominant in the soils and when low magnesium concentrates, that is less than 10% of soil saturations, are seen. A common magnesium deficiency problem in cattle is grass tendency or hypomagnesium due to insufficient of magnesium in foliage. Livestock can be fed magnesium salts in low magnesium areas, or soils can be amended with Epsom salts or dolomite additions. Because of the low solubility of dolomite, at pH levels above 7, spraying dissolved or dry Epsom salts is usually the most suitable on high pH soils. So let us look at the various commercial forms of magnesium fertilizers. Firstly, there is dolomite. This is 13% magnesium and 21% calcium. It has the advantages that applying it will give you the increased concentration of two required nutrients, that of calcium and magnesium. It also enables a pH correction if that is required. The disadvantages are that it's relatively insoluble and it takes a long time to react. Magnesium oxide at 54% magnesium is another product you can consider. This has the advantage that it has a high concentration of magnesium, but it is relatively insoluble and again takes a long time to react. There is a potassium manganese sulfate product that you can look at. This has 11% manganese, 18% potassium and 22% sulfur. Therefore, you're giving a range of nutrients to your plants, and it is relatively soluble. A disadvantage is that it dissolves too slowly to be used in a solution form. Let us now move on to the compound sulfur. Plants require as much sulfur as they do phosphorus, one of the most important elements. Sulfur is found in the compound cysteine and methionine, amino acids, and it is also required in some protein constructions. It activates certain enzyme systems and is a component of some vitamins, for example vitamin A. Sulfur is found in mustard oil glucosides, which impact characteristics, odors and flavors to such plants as mustard, onions and garlic. Sulfur fertilization has been shown to increase the seed-soil contact of crops such as soybeans and flax. Plant animal scientists have shown that plant tissue content is typically 1 per sulfur for every 15 to 20 parts per million for the optimal growth of animal feeds. Sulfur is essential in the manufacturing of chloroplasts. This is where the light reaction in photosynthesis occurs. Sulfur is also found in the iron-sulfur complexes of the electron transport chain in photosynthesis. Again, this is part of the light reaction, the capturing of energy from the sun. Sulfur is immobile, and deficiencies therefore affect younger tissues first before they will affect older tissues. Symptoms of deficiency including yellowing of the leaves and stunted growth. The preferred level of sulfur in the soil is between 10 and 20 mg per kilogram of soil. The requirements for the crop varies very much with the crop. Let's look at sulfur deficiency symptoms. It is not common in grapevines and it usually causes chlorosis, therefore the leaf looks yellow-like. Efficient nitrogen utilization requires adequate sulfur because both are needed to form the proteins in the plant. Insufficient sulfur inhibits protein synthesis, causing nitrogen to accumulate in the plant as nitrate, amides and amino acids rather than the protein. Research has shown that sulfur plays an important role in crop quality such as bread-making quality of wheat and protein content of forages and grains. Bread-making varieties of wheat have approximately 10% more sulfur in the grain than non-bread-making varieties, although a total plant sulfur uptake is similar. This was according to Redding in 1986. Two important factors related to bread making are low volume and dough extensibility. Both of these factors are directly related to sulfur concentration in the grain, which in turn is dependent upon available sulfur in the soil, as shown by Urger et al. In 2002. As a constituent of amino acids, sufficient sulfur is essential for high protein content in forages and grain. Sulfur undergoes numerous transformations in the soil, including biological, chemical, and atmospheric processes similar to that of the nitrogen cycle we covered in Lecture 6. Only a small fraction of the total sulfur in the soil is readily available to crops. The major processes governing sulfur availability in the soil are plant uptake, mineralization, immobilization, exchange, volatilization, precipitation, oxidation, reduction, mineral weathering, and leaching. Management of sulfur is improved by an understanding of how the nutrient cycles in the soil and under what conditions deficiencies are likely to occur. Crops can uptake adequate amounts of sulfur in the soil with soluble sulfate or gypsum concentrations above the critical level of 5 to 10 parts per million in the top 10 centimeters or so of the soil via mass flow. Soluble sulfur usually represents less than 10% of the total sulfur in the soil and is replenished by mineralization of organic matter, weathering of mineral sulfur, oxidation of reduced sulfur, and desorption. A plant nitrogen-sulfur ratio of about 15:1 is ideal for the effective protein synthesis. Ratios higher than this suggest that protein synthesis is being limited by lack of sulfur, where smaller ratios imply surplus sulfur, which is retained as soluble sulfur within the plant, as mooted by Stewart and Porter in 1969. In this way, nitrogen-sulfur interactions are positively related and should be managed together. No response to sulfur additions will occur if nitrogen is limiting plant growth. Similarly, an optimal sulfur level maximizes the effect of nitrogen fertilization on yield, although actual nitrogen uptake in the plant does not change, as shown by Razumin et al. In 1975. Sulfur dioxide, SO2, and hydrogen sulfide, H2S, from the atmosphere can also represent significant sources of sulfur for plants in locations downwind from coal-burning plants, metal smelters, or geothermal areas and some urban areas. These compounds are beneficial only in low concentrations and are absorbed by the plant leaves through stomata. Atmospheric additions to crops and soils range significantly, but are usually between 3 and 10. Crop residues contain considerable amounts of sulfur because the nutrient is incorporated into the plant material and is not easily released. As is the case with other nutrients, the plant material removed at harvest can represent a significant loss of sulfur from the soil. In forage crops, such as alfalfa, where there is a high sulfur uptake, most of the biomass is removed, resulting in a major loss of sulfur after that crop is grown. On the other hand, in canola, only about 15% of the total plant solar is removed from the soil with the harvested seeds, so most of the sulfur remains in the residue, as shown by Jackson in 2000. Grazing foliages on site can significantly reduce sulfur losses because livestock release more sulfur back into the soil. In fact, as much as 90% of sulfur consumed by sheep is released back into the soil, as shown by Teasdale et al. In 1986. Mineralization and immobilization cycles occur in sulfur. Organic sulfur compounds held in the plant, animal, and microbial residues collect in the soil organic matter and represent the largest sulfur pore in the well-developed grassland soils. Over 90% of the total soil sulfur in certain regions can exist due to organic form. This was shown by Halvenden in 1999 in the US. There is an exception to this, however, and that is when soils have a mineral sulfur accumulation of gypsums, and this accumulation is significant. Microorganisms decompose the organic matter and release plant-available sulfur through the processes of mineralization, which occurs similarly to that of the nitrogen cycle, see Lecture 6. About 1 to 3% of organic sulfur is mineralized each year, contributing to about 4.8 to 15.6 kilograms per hectare of soluble sulfate for plant use annually. The amount of sulfur made available to plants annually via mineralization depends on the amount of organic matter in the soil and the concentration of sulfur in the organic matter. Therefore, taking steps to maintain or increase organic matter with such strategies as no-till, minimum till, or organic additions can help supply a relatively constant amount of available soil in the soil by using the natural soil cycling. Immobilization refers to the process of converting inorganic sulfur to organic sulfur and is easily and reversible of mineralization. Microorganisms remove available sulfur from solution and converted into proteins and other organic compounds. Although this process does remove sulfur from the available pool, the sulfur is still in a reserve pool that could eventually become available to plants via mineralization. Since mineralization and immobilization are primary biological processes, any factors affecting microbial growth will influence both the sulfur transformations. Important factors include soil temperature, water content, pH, carbon to sulfur ratios, aggregation, and residue composition. The highest mineralization and immobilization rates will occur under aerated, warm and moist conditions with near neutral pH levels, because these conditions are optimal for microbial activity. The nitrogen-sulfur ratio is relatively stable in organic matter, remaining near to 8:1, as shown by Forth and Ellis in 1997. But the carbon to sulfur ratio is more varied and strongly reflects the relative amounts of mineralization and immobilization processes that are occurring in that soil ecosystem. If residues and organic matter lack sufficient amounts of sulfur, microbes will pull the needed sulfur from the soil and immobilize it, meaning that your plants will not be able to access it. Residues with carbon-sulfur ratios higher than about 400:1 result in net immobilization of sulfur from the soil, while carbon-sulfur ratios lower than 200:1 result in net mineralization of sulfur in the soil. This was shown by Fenray in 86. Between ratios of 201 and 401, a combination of these processes does occur. The carbon to sulfur ratios of a number of organic residues are listed in some texts, and you can certainly refer to these as a guide, or you can speak to local companies that supply commercial fertilization, and I'm sure they'll be able to help you work out what is the best system for your particular soils. Do you have mineralization? Do you have immobilization? And if you have these processes, what do you do best to manage your available sulfur? The last process in the sulfur cycle I wish to talk about is biological volatilization, and this can occur both in aerobic and anaerobic conditions. That means wet or dry, with or without oxygen. This biological volatilization is less significant in well-drained, well-aerated soils, as shown by Teasdale et al. In 86. Probably the most significant volatile loss of sulfur occurs when agricultural areas are subject to fire. Although sulfate concentrations may increase due to chemical mineralization, that is, burning of organic sulfur, burning dry grass has resulted in losses of up to 75% of total sulfur in vegetative cover, again shown by Teasdale et al. In 86. The conversion of organic sulfur to inorganic sulfur by burning may also make the nutrient more soluble to leaching. Inorganic sulfur occurs in solid phases in the soil as sorbed soil or sulfur minerals. Sorption of SO4 increases an anion exchange capacity. Anion exchange capacity is often abbreviated to AEC. Soils dominated by positively charged iron or aluminium oxide clays will have a high ion exchange capacity and therefore sorb significant sulfate. In some regions, soils typically have low ion exchange capacities because of their strong net negative charge and high pH levels, so sorption of sulfate is minimal. As a rule, SO4 sorption is insignificant above a pH of 6.5. Inorganic sulfur minerals such as gypsum represent an important sulfur pool in some soils. Commonly, gypsum accumulates in the subsoil, forming a sulfur-rich layer often in close proximity to calcium carbonate layers. Although the sulfur layers of these soils may have low levels of plant available sulfur, the deeper mineral sulfur maintains an adequate supply of sulfur within the rooting depth of most crops, as shown by Beaton and Soper in 1986. Early in the growing season, subsoil sulfur may not be available to crops because it is out of reach of the growing roots. Later on in the growing season, when the soil water is usually moving upward through the profile and plant roots have grown deeper, adequate soil can be generally accessible to the crops. Sulfur occurs in numerous primary and secondary minerals which release sulfate and sulfide as they weather. Gypsum is widely distributed in arid and semi-arid soils where precipitation is too low to reach the mineral out of the profile. Schlays and clay stones in certain regions containing gypsomes release plant soil available sulfur as they weather, as shown by Versyth and Montague in 1980. Ore deposits can contain metal sulfides such as iron, zinc and manganese sulfides. As the sulfides S2 are exposed to oxygen and water, they oxidize to sulfates and can significantly lower the pH of the surrounding soil or water, as the case with acid mine tailings. In agricultural settings, the slow release of sulfide minerals into the soil can be beneficial, but excess acidity may be of a concern. Elementary sulfur also oxidizes to sulfate in the presence of water and air and is commonly applied to high pH soils, both as sulfur fertilizer and as the means of lowering pH for plant growth. The resulting acidity is generally short-lived in well-buffered soils and requires contained application to be maintained. Gypsum added to the soil as a fertilizer will neither rise nor lower the pH of the soil because the sulfur is already completely oxidized in the form of sulfate. Sulfides and elementary sulfur are found in waterlogged soils and wetlands and generally exist in low concentrations in many agricultural soils. Sulfur is lost from the soil by two processes other than the crop uptake. These processes are leaching and volatilization. Leaching is the physical removal of the plant available sulfur by water moving through the profile, whereas volatilization represents a biochemical or chemical transformation and subsequent release of sulfur into the atmosphere. The areas with higher risk for sulfate leaching are associated with higher precipitation, irrigated conditions, coarse textiles, shallow soils, and soils with low AEC. Irrigation following sulfur fertilization application can move SO4 through a profile and eventually out of reach of the plant roots. Therefore, you have to be mindful about how you add this compound. Sulfate leaching represents an economic loss because once the sulfate has left the soil system, it is no longer available for crop uptake. In semi-arid climates, sulfate often collects in the subsoil, as described earlier, because there is insufficient water to flush the anion below the rooting zone of the plants. Leaching losses are generally less in high pH soils because sulfate will precipitate with calcium or magnesium. It should be noted that in some soils, water moving upward through the soil profile via capillary action late in the growing season can carry sulfur towards the plant roots and the soil surface. In such instances, excess calcium magnesium sulfate salts can accumulate to harmful levels in the surface and limit plant growth. Careful water management, especially in irrigated cropping systems, can prevent many of these problems. Volatilization of sulfur compounds results in relatively small loss in agricultural soils. Generally, the amount of sulfur volatilized from the soil is less than 0.05% of the total sulfur in the soil, and most live plants, the release is between 0.03 and 6% of the total sulfur in the soil, as according to Halvlin et al. In 1999. Most volatilization in the soil occurs during biological decomposition of organic residues. So, what form do sulfur fertilizers come in? Well, you can commonly come across sulfate or potash, K2SO4. This has about 18% sulfate and about 41% potassium. The obvious advantages are that it contains both potassium and sulfur. Disadvantage is that it is more expensive than some other products that are available. Ammonium sulfate is another option that you can use, and this contains 24% sulfate and 20% nitrogen. It has the advantage that it can supply both nitrogen and sulfate, but is usually supplemented with other nitrogen fertilizers, and this can make it limiting. You can consider gypsum. This is 15% sulfur and 19% calcium. It contains both calcium and sulfur nutrients and enables the reduction of flocculation in clays. That brings us to the end of part 1. So when you review this lecture, look at how each of these secondary macronutrients are used by the plant. Consider the basics of the cycle. I don't expect you at this level to understand all of the components that I have been describing, but taking out the basis that compounds can be cycled and that understanding their chemical properties can help you with managing these secondary macronutrients. Understand and have an idea about how you can commercially add these macronutrients in the form of fertilizers. What are these fertilizer options and what are the advantages and disadvantages? Ensure that you can compare and contrast the differences of the macronutrients that you are detailed here with that found in lecture 6. That brings us to the end of this lecture, part 1. Please now go on to watch part 2 of lecture 7.